Hi, my name is Andrew, and I work on program analysis at Google. Today I'm going to give a summary of improvements to DFSan in the last year. So first, what is DFSan? DFSan, or the Data Flow Sanitizer, is a dynamic taint analysis tool. It consists of an instrumentation pass in Clang and a runtime library in compiler-RT. It tracks tainted bytes through an execution. This is useful for answering questions like, where does sensitive data flow to? Or what code operates on tainted data? So DFSan provides an API so you can control which bytes it should consider as tainted, and you can ask it which bytes are tainted at another point in the program. So this talk covers September 2020 to September 2021. The main improvements in this time are switching to the FAST8 taint tracking data structure, adding support for origin tracking, memory allocation improvements, false positive fixes, and some other miscellaneous improvements. So the rest of this talk will be going into more detail of each of these. First, I'd like to acknowledge that most of the work I'm presenting here was done by others. So credit to my colleagues at Google, Janzo, George, and Matt. I'd also like to acknowledge that we're building on an earlier version of DFSan and leveraging code from other sanitizers, particularly MSAN. So FAST8 mode. So prior to FAST8 mode, the existing one we called legacy mode. So legacy mode supported 2 to the 16 labels. It used 2 bytes of shadow memory per 1 byte of application memory. And these 2 bytes of shadow memory were used to hold a 16-bit index into a table of taint labels. And legacy mode has now been deprecated and deleted. So FAST8 mode, for contrast, supports 8 labels at a time. Each byte of application memory has 1 byte of shadow memory. And each of the bits in the shadow space represent a different label. So you have bit flags for different labels. This means that we can combine labels with a bitwise OR, but it also means we need to run the program multiple times to track more than 8 things. So to illustrate this, in legacy mode, we have 2 bytes of shadow memory for each 1 byte of application data, and the shadow memory contains an index into a table of taint labels. So at a point in the program, like for instance, this statement where int r is assigned, we're actually combining 2 tainted values. So the resulting value will have a new taint label, which is kind of the union of both. So in this case, the instrumentation would need to allocate another label in the label table. So with FAST8 mode, we have a 1-to-1 shadow, and each byte of shadow memory contains the taint label for the corresponding byte of application memory. So here the DFSan set label API is simply setting the value of the shadow memory, and the DFSan get label is simply allows you to read that value out of the shadow memory. So next, origin tracking. So if DFSan finds that some byte is tainted with a label, then the next question is going to be, how did that byte become tainted? And this is where origin tracking can help. So origin tracking will use 1 extra byte of memory to hold origins for each byte of application memory. This implementation is based on MSAN's origin tracking, and it records a coarse information flow about a value flow. So it will sort of build a chain of markers, starting with the DFSan set label, and it'll add a link for each store instruction, and optionally also for loads. And each link in the chain, it will capture the current stack at the point of that link. origin tracking will only be used for more than 4 bytes of data, which is contiguous and tainted with the same taint label. So the reason for this is the origin tracking uses 32-bit IDs to refer to the link in the chain. So this 32-bit ID is stored across 4 bytes of origin memory. So the X here is a 4-byte integer, so we can fit the origin ID. If the data wasn't 4 bytes wide, we simply wouldn't track the origins for that. And this is an example of the output for origin tracking. So reading this output from the bottom up, we have the taint value created at a set label. Then the taint value is stored when the vector is constructed. And then the another taint value is stored again at the statement where R is initialized. So next, memory allocation. So the memory layout in DFSan now matches MSan. Initially, DFSan used a simpler memory layout, but we saw some bugs where heap allocations occurred in a region of memory that we weren't expecting. So we switched to MSan's memory layout to make it more robust. We also made a lot of fixes for releasing memory that's no longer needed. So the old implementation leaked a lot of shadow memory. Like running it for a long time would lead to the process with hundreds of gigabytes. So now it's much, much better. So now DFSan uses the sanitizer allocator. So the freeing memory will also release shadow and origins memory. We added a munmap wrapper, which will also knows how to release the shadow and origins for freed memory. And as an optimization, writing 0 labels to shadow can now also release those pages. So if a shadow or origin page of memory is all 0, then it won't be resident. So we want to try to release as many of those as we can to keep the memory usage down. So false positive, so some false positive fixes. Previously, DFSan couldn't track individual elements in composite data structures. Oops. And now it can. So previously, the 42 and the X here would share the same taint label, whereas now those two values can be tainted independently. Another bug was the select inst propagated taint from its condition. So select inst should only propagate taint from either of the two values. A more subtle bug was needing to clear TLS after a signal callback. So DFSan uses thread local storage to carry taint labels between functions. And when a signal handler is run, the code inside the signal handler could also use TLS to propagate taint labels. So this would mean that when the signal handler exits, the TLS values would still have taint bits set during the signal handler. So we need to clear out the TLS after a signal callback to avoid false positives. Another known bug is overtainting around vector bool. So the problem here is the vector bool specialization packs 8 elements into 1 byte, but DFSan only supports 1 label per byte. So DFSan will end up conflating the taint labels for the 8-bit elements that are packed into the same byte. We looked into solving this problem by removing the specialization, but we didn't find a good maintainable solution here. Some other miscellaneous improvements. We changed the prefix from from a DFS dollar prefix to a .dfs suffix to improve demangling support. We also removed a lot of dead code for unsupported platforms, fixed a variety of clang tidy warnings, added more functions to the ABI list, added more test cases, and improved documentation. So some future work that we have in mind, adding support for control flow tainting. There's cases where a value has an implicit dependency via control flow rather than explicit dependency. So this can be useful for finding out what information about sensitive data is leaked if the sensitive data itself is not leaked. So this is something that we might do by reserving 4 bits in the taint label to represent a implicit dependency. Another piece of future work is continuing to converge with MSAN. So DFSan and MSAN now work in a very similar way. So there should be more opportunities here to share code. And in conclusion, DFSan has grown more efficient and more robust. So DFSan can now provide useful results on some of Google's largest C++ binaries with reasonable overheads. And we're also finding that overtainting issues have mostly been addressed. So thank you for listening.